Okay, very good morning to everyone, and I thank the organizers for this opportunity. So, I'm going to be talking about localization and universality of 3D pseudospin fermions, and we'll see what this means. But before I begin, let me thank Arpan, and this work has been done by Arpan. So, if there are mistakes, you know whom to blame. So, and I also thank ANRF for their funding. So this talk is going to be based on our recent work, and it just got accepted today. The problem that we are trying to address is like something that has been talked about since many decades, and that's the problem of what happens when electrons move in a disordered potential. So classically one expects diffusion to take place, but that doesn't happen. We know that now because of quantum effects. We have Anderson localization, and so many strides have been made in this field since then, after Anderson, and some of them were again by Ramakrishnan and others who proposed the scaling theory of localization, and then we had others who talked about weak anti-localization when you have spin orbits coupling and so on, and then we had the problem of like strong disorder, how to treat it analytically, and that was done by Fatov and others using supersymmetry and other methods. And then weak anti-localization in graphene was discussed by Suzura and Ando even before actually graphene was experimentally discovered. It used to be called 2D graphite. And then there have been many more works, trying to synthesize disorder and topology and look at what happens when these two things combine. And of course, this list is not exhaustive. There are many more. So I'll just begin by reviewing what we mean by a weak localization correction. So imagine that you have your quantum state that can move on the Fermi surface, and it gets kicked due to disorder, so it changes momentum, and then one can imagine that there is some sort of a backscattering that can happen due to multiple scattering events. And of course there are a lot of paths that can lead from k to minus k, but one particular path is non-trivial, and that's exactly the time reversal copy of the path. And so what happens in this is that the sequence of momentum transfers, it happens in right and the opposite direction. And as long as you have time reversal symmetry, one can always argue that such a path is going to exist. And when you sum the amplitudes of corresponding to all the paths, so most of them cancel out with each other, the phases cancel out, but these two phases do not cancel out as long as our scattering is phase coherent. Okay, and so then these two phases, they can constructively interfere, and there's an enhanced probability of backscattering. Okay, and this is what is like the first correction to conductivity, also known as the weak localization correction. To see these effects in experiments, you can do magnetoconductance experiments at weak magnetic fields, where one of these phases, because magnetic field breaks time reversal symmetry, so this one of these effects, so these phases are not going to add up. But what can happen is that the quantum state can also acquire some non-trivial phase along its path. So you can imagine that if it's a spinor, that spinor can rotate somehow, and that's what happens when you have, let's say, spin orbit coupling, or if you have some Berry phase in your system. So then these two paths, they have a destructive interference, and there's a reduced probability of backscattering. And so as I mentioned, these effects can be probed in magnetoconductance experiments. So positive LMC would mean that there is localization, and negative means anti-localization, and so on. Okay, so let me move from this to discussing some novel excitation in solid, because combining this and localization, that's our main motivation. So of course Weil and Dirac fermions have been very popular over the last 1 or 2 decades because of their interesting properties, and their analogs exist in high energy physics. But in solid crystals we can have excitations that can actually go beyond the naive Weil and Dirac fermions, and that's so certain symmetries can stabilize multifold band degeneracy. So you can have 3-fold, 4-fold, 6-fold degenerate point, and the low energy description it can be thought of as a chiral Hamiltonian, which is characterized by an effective pseudospin. Okay, and interestingly, these have no counterparts in high energy physics, because there's greater symmetry there, but the symmetry is more restricted in crystals. So these fermions, they carry a high topological charge, and they can also have many unconventional properties, optical as well as transport properties, that go beyond the simple and Weil fermions. And for example, even chiral anomaly, which is sort of well understood in for your spin half Weil fermion, that can look very different for even a simple spin 1 fermion. And so many of these systems have been proposed, and some of the signatures have been also seen in experiments. Okay, so the question that we're trying to address is the following: that how does quantum localization evolve along the full pseudospin S hierarchy? So there are 2 aspects to it. One is the weak localization correction that I talked about, and the other is the strong localization, which is of course a much harder problem. So this talk is going to be just devoted to the study of weak localization corrections in pseudospin S fermions. So spin half and spin 1 have been actually studied in isolation by earlier works, but so we wondered if there is if we can develop a unified analytical framework that can treat an arbitrary pseudospin S. So that has been missing so far, and the reason is that it may shed some insights into the physics. So in particular, our objectives are to extract some semi-classical transport coefficients and identify the surviving diffusive Couperon modes. I'll talk about them more. Compute the localization correction, and also see the effect of interband and intervalley scattering, because as your pseudospin increases, for example, when you go to pseudospin 3/2, you have the effect of interband scattering can actually matter a lot. Okay, and we want to do this in a unified framework that works for any spin. So that was the goal. So we start with a low energy description of our system, which is just a spin that is coupled linearly to momentum. So Hamiltonian looks like S dot K, and so the S matrices here, they are just 2s plus 1 dimensional matrices, which are just higher dimensional general representations of the SU2 algebra, which is basically given by this commutation relation, and that's just spin conservation here. Okay, and so the energy eigenvalues are surprisingly simple. So S prime, so you have linearly dispersing cones, just like you have for your standard Weil fermions, but now there are multiple of them. And in addition, if I have integer pseudospins, I also get a flat band in the middle, okay, which is absent for half integer pseudospins. So S actually means your chirality here, or the pseudospin, and S prime are the various bands, which you can also call as helicity. And the quantum and the eigenmodes are basically the helicity eigenstates. which assume this form, and this form is particularly nice because these coefficients here, these are nothing but reduced Wigner functions. So so from your quantum theory of angular momentum, you can actually get neat analytical expressions for an arbitrary pseudospin and helicity eigenstate. Okay, so this actually allows for more analytical treatment further. So just to, as a side comment, we see that each eigenmode actually is a summation of many coherent projections here, and as you increase the pseudospin, we see that the spinor becomes more and more semi-classical. So the near backscattering, so backscattering is suppressed for all of them, but near backscattering is actually exponentially suppressed as you increase S. So it just becomes like a classical arrow in that in the high S limit, and the phase winding also increases with the increasing S. Okay, so that's our system, and so for this order, we assume a delta correlated disorder, and so we have these impurities randomly placed in the sample. And additionally, we have this matrix M here because so unlike earlier works which assume just the presence of only scalar or diagonal disorder, where this M is an identity matrix, we wanted to take the more general case where M is the square matrix and which has off-diagonal elements, and because it has off-diagonal elements, you can have various bands that can talk to each other now. So in other words, your disorder can actually flip the helicities as well. So that's something that we allow for. And to make further analytical progress, we can actually expand this disorder matrix in terms of this irreducible tensor operators, which are called T here. And the matrix elements of T again can be computed from your angular momentum theory by Wigner and others. So the matrix elements of these tensor operators are just related to this Wigner's 3J symbol, so this stuff in the brackets which you see, and which is actually also related to the Klebsch-Gordon coefficients. Okay, so we have the system, and the disorder is specified, and because of this, the existence of these analytical forms, we can then calculate various quantities that are relevant for transport, for example the self energy and the scattering time in a closed form, which for an arbitrary disorder, which and in the limit of scalar disorder we recover the standard expressions, and same goes with our transport lifetime as well. Okay, so now let's so the role of disorder, it obviously broadens the quasi-particle spectrum, but it also renormalizes the current operator. So because of multiple scattering, so the current operator is just electric charge times this v cap, which is this velocity operator, because J is just E times V. But because of multiple scatterings, this operator is renormalized. Okay, and so that leads to this Bethe-Salpeter equation, which is actually, you can see it's given by this diagram. So this single line is an impurity line, and then this equation just computes the effect of multiple disorders. So that's just the same thing written in equations. And so usually when you solve such an equation, a simple ansatz like, so capital gamma is addressed, vertex, and small v is the bare vertex. Okay, but so typically when we solve an ansatz like gamma is a scalar times v works, but not here, because our disorder matrix can actually couple various channels, so it's not a simple diagonal matrix. So we can therefore expand this vertex into spherical harmonics and then actually calculate, and that also again allows to calculate these factors for arbitrary helicities with some neat analytical forms. Okay, so now let's come to the quantum corrections to the conductivity. So as I mentioned that so you have to go from R to, let's say electron is going from R to R prime, it can actually go via this path or via a time reverse path. And so if you want to compute such a propagator, you can do this. So that propagator is known as a Couperon. So that's just computing this probability which describes this dynamics of these two particles moving along time reverse path. Okay, and so this thing here is just our bare vertex or the bare Couperon, and this gamma naught, and this gamma is our dress Couperon, and that's again the Betti-Salpeter equation that one needs to solve. So in the end, these coefficients C, M, and P are the one that we actually need to compute, and that gives us this Couperon propagator. And so that can tell us something about the nature of the localization corrections. So as you can see that there are many such modes here, M, N, and P, where incoming and outgoing momentum, and so which of these modes actually become important is the ones that diverge in the long wavelength limit, because those are the ones that give rise to the localization channels. Okay, so that's what is the signal that our diffusive transport kind of becomes unstable, and you have this localization correction. Okay, so after you solve the Betti-Salpeter equation for each of these channels, so each of them actually take this particular form, okay, 1 over q square plus this capital Q square, small q is just the momentum of the Couperon. And what we find is that for all the channels except when p is equal to 2s, the Couperon actually acquires a finite mass or a finite gap. Okay, so that means so only when p is 2s and mn is 0 we have q equal to 0. So that's the most diverging contribution that is coming from this Couperon propagator. So out of all the 4s plus 1 channels, we have only one channel that is actually diverging in the diffusive limit. Okay, and that's what is given by this, and this capital D S prime is just a diffusion constant. Okay, so that's kind of interesting. So once we have done this, we then just need to plug this into these diagrams here and calculate. So these are the Hikami, these are known as Hikami boxes, and these will actually give you the correction to the conductivity, or the localization correction to conductivity. Okay, and so after doing the calculations, this is what we find, that this is my correction to the conductivity. And the interesting thing that we find is that this quantum correction is actually, if you just look at the magnitude of this quantum correction, so this phase factor, it doesn't make a difference. So just the magnitude is actually independent of S and S prime. So it doesn't depend on which chirality or which pseudospin you're talking about, or what is the helicity index. It's totally independent of that. Okay, and that magnitude is actually identical to the magnitude of conventional Weyl fermions and also a standard 3D electron gas. Okay, so that was a first interesting result. And if you look at this phase factor is just exponential I pi times 2s. So that just alternates signs when you have a half integer or an integer pseudospin. Okay, so the magnitude is independent of chiralities or helicities, but the localization, it depends on the chirality or the pseudospin. Okay, so systems with half integer pseudospins give rise to weak anti-localization, and the integer pseudospin give rise to weak localization because the sign actually flips in the other case. Okay, And so the sign is actually, if we examine, is also related to this time reversal operator, so which is given by this particular form. Kappa is just a complex conjugation, and the square of the time reversal operator is just minus 1 to the power 2s. So that also alternates signs as s goes from integer to half integer, and the sign of this correction actually is given by the sign of the square of the time reversal operator. Okay. So that means, so if you talk in terms of Wigner-Dyson class, symmetry class, so for integer pseudospin, these belong to orthogonal symmetry class, and the half integer belong to the symplectic symmetry class. One can also compute the Drude conductivity, and what one finds is that, of course, the Drude conductivity, it's dependent on chirality as well as helicity. So it's but the quantum correction to the conductivity, it has this universal feature. So it is independent of. So those are the green dots if you see here. Okay. So far this universality is there, but this universality is fragile because we have assumed scalar diagonal disorder when we computed, but with no intervalue or intraband scattering, but that can be done, as I had mentioned, and because the disorder can, in principle, couple various bands and valley indices to each other, right? So for example, if you just have a fermion of a particular chirality, by the Nielsen-Denomia theorem, you must have another valley somewhere with an opposite chirality. Okay, and if you go to 3/2 or higher pseudospins, then of course you have multiple bands that become relevant for transport. So the problem is then to attack, have multiple bands and multiple valleys. So then this Couperon propagator, this capital gamma, it is no longer a single scalar, but it instead becomes a tensor in this combined valley and spin space. So because different scattering processes can actually mix these channels with each other. So then the particular Betis-Salpeter equation is actually it becomes you cannot just use the same ansatz that we do for a scalar disorder. So then what we can do is we can so these are, for example, our equations for the dressed vertex, and M and N are basically indices that are in the combined valley and band space. And the way to solve it is using an iterative method. So small gamma is your bare this Couperon. So we can substitute this small gamma and compute the dressed vertex, and then repeat this process until we find that the angular structures basically converge on both sides. So these things are basically they are functions of theta and phi, which can have a multiple expansion. So we need to basically come up with an ansatz such as that it's satisfied at both ends of the equation. So as a demonstration, we did this explicitly for 3/2, where you can see we have actually 4 relevant channels where scattering can let's say preserve the valley as well as the band, or it can preserve the band index but change the valley index, or preserve the valley and change the band, or it can do both. Okay, so there are 4 possible scattering channels here, and once you compute then the magnetoconductivity after going through the calculation, we find that in each of these cases there is a crossover from weak anti-localization to weak localization as you increase that particular channel strength. So eta I here, it represents the strength for let's say, so in this figure you are considering intervalley intraband channel, so eta represents that strength, and the eta corresponding etas represent the corresponding scattering strengths in each of these. Okay, so as you increase the scattering strength, the magnetoconductivity actually changes sign at some critical value, which signals a crossover from anti-localization to localization. And so if you want to, we wanted to qualitatively understand, because the critical value is actually not the same for each of these. It really depends on which channels, and it's very non-universal. So one way to kind of estimate is that you can compute something called as the backscattering probability for each of these channels, and we find an inverse sort of a relation between this critical strength of the scattering as well and the probability. So yeah, just a minute. And that brings me actually to the last slide. So what we have done is we have developed a unified theory of semi-classical transport and quantum interference for three-dimensional chiral fermions for an arbitrary chirality. And of course, the Drude response is strongly dependent on the chirality and the helicity, but the leading correction has a universal magnitude, and that's identical to that of conventional Weyl fermions or conventional diffusive metals, and the sign is just determined by the parity of 2s. Okay, and so, but this universality is fragile because interband and intervalley scattering, they can actually make this Couperon multi-channel, and we don't have any universal features then. And that's what we demonstrated explicitly for spin 3/2. And of course, future works will like to explore the fate of strong localization in this system, but that's something for the future. So with this, I would like to conclude, and thank you.
Thank you. So now the session is open for questions. Any questions?
So what's the experimental prospect? You have developed a theory, but if you want to see the quantum correction to Drude conductivity,
right. What you can do, you can look at the cusp of these magnetoconductance experiments, and that might, because that's the only way you can probe. So that cusp may give you some universal features. Yeah.
Anymore? Okay.
Thank you.
Thank you, Gargi Sharma. So that's next.